Good morning, students. In this lecture, we will be seeing the stress and strain. So first we shall see what is a strain. So when a body is subjected to any external force, when a body is subjected to external force, see, this is your body, it is subjected to an external force. So when his body is subjected to an external force, there is change of dimension of the body. There is change of dimension of the body. I am applying a pull. So these are two equal and opposite forces. So if you apply this force, what happens is the body will be elongated from the initial position to this final position. So initially you may have the length as L. After the application of force, what happens is the body gets elongated and its length changes from L to L plus delta L. So the final length is L plus delta L and the initial length was L. So the length changes from L to L plus delta L. The strain is indicated by the letter epsilon or the letter E. So this is called as epsilon. It is denoted by the letter epsilon or E. So the strain is given by the change of dimension. So what is the change of dimension? So this delta L is the change of dimension. The change of dimension to the original length. So I can define strain as the change of dimension to the original length. This may be also called as longitudinal or linear strain. First of all, we should know what is a longitudinal or linear strain. Linear strain or longitudinal strain. So in the previous diagram, you have considered a body and that was subjected to a force. What this linear strain is, you have to understand the axial loading concept. See, this is your body, and this is the axis of the body. So, this is the axis of the body. So, when a body is subjected to an axial load, either it may be a tensile or a compression force. I am considering a tensile force. So, when a body is subjected to an axial load, so this force P is your axial load. This acts along the axis of the body. So, what happens is there is a change in the length of the body. So, what happens? There is a axial deformation. So, from this position, it changes to this final position. So I can define the longitudinal or linear strain according to the definition, previous definition, as change in length by original length. So the longitudinal strain see, generally speaking, when you hear the term strain, you say delta L by L. So this is the formula which you have studied in the previous classes or in your higher secondary schools or in 10th you have studied this concept that strain is equal to the change in length by the original length. But now we have to understand what is linear strain and lateral strain. So to understand the linear strain, consider this body subjected to an axial pull. So this force is acting along the axis of the body. According to the definition, the change in length to the original length is said to be a strain. So this strain is actually the longitudinal strain. So this strain is actually the longitudinal or linear strain. So why I am saying it as a longitudinal or linear strain? Because it is the ratio of this delta L is the axial deformation. If the deformation acts in a direction which is parallel to the direction of the applied load, then it is called as a longitudinal or linear strain. So this longitudinal or linear strain may be classified as tensile and compressive strain. Tensile strain or compressive strain. First we shall see what is a tensile strain. So in the linear or longitudinal strain, you can consider tensile strain and compressive strain. So in a tensile strain, what happens is the length increases. So initially, I am having a body of length L which is subjected to two equal and opposite forces. You can say it as a pulling force. So what happens is the length changes from L to delta L. L plus delta L. So the length changes from L to L plus delta L. So tensile strain is given by the change in length by the original length. So this delta L is the increase in length. Generally speaking, if you say strain, it is a change in the dimension to the original dimension. But if you are speaking particularly of a tensile strain, then what happens? The length increases from L to L plus delta L. So this is your initial length and this is your final length. So the length increases. So in a tensile strain, you can say this is the ratio of increase in length to the original length. Now, compressive strain. The compressive strain is defined as the ratio of decrease in length, decrease in length to the original length. I am subjecting a body to two equal and opposite compressive forces P. So what happens? Initially, the body length was L. So after the application of the force, the body changes to this position. So initially, I am having this length up to 1. After compressive force, the body length will change to L minus delta L. So if you consider this as delta L, your final position will be, your final length will be L minus delta L. So initial position was L, and after the application of a compressive force, the length changes from L to L minus delta L. So I can define compressive strain as the decrease in length. So that is delta L divided by L. So this delta L is the decrease in length. Whereas in the case of a tensile strain, this delta L is the increase in the length. Next is the shear strain. For understanding this shear strain, you consider a rectangular body like this, which is fixed at the bottom. You name this as A, B, C, and D. Since it is a shear strain, we have to apply a shear force. So I am applying a force P parallel to the face AB along CD. Now what happens is the shape of the body changes. So finally you can expect a shape like this, shown as a red. So this red color lines is the position after deformation. So let me corner points as D1 and C1. So the initial position was A, E and D, and the final position is A, B, C1, D1. So on changing the shape from ABCD to AB C1 D1, what happens? The angle changes. You call this angle as pi. So what happens to tan pi? So tan pi is equal to opposite side by adjacent side. So what is your opposite side in the triangle ADD1? So the opposite side is D1 divided by adjacent side is AD. So DD1 you take this as DL and this ADS H. So DD1 is DL and AD is H. This angle pi is normally very small. So if pi is very small, if pi is very small, you can say tan pi is equal to pi. So instead of tan pi, I can write it as pi is equal to dl by h. What is this dl? This dl is the transversal displacement. Shear strain you can call it by pi, or you can either use the letter E S. So both are shear strain. You can indicate by either pi or ES. So shear strain pi is given by the ratio of transversal displacement to the height h. So this height h is the length AD. Volumetric strain. Volumetric strain, it can be denoted by EV or epsilon V. Volumetric strain is the ratio of change in volume to the original volume. Consider a block like this. I am subjecting this block to compressive forces in all the three directions. So what happens if you compress a body? The volume changes. So from this initial position. So this is your initial position. From this initial position, your body changes to this final position. So, since you are subjecting to a compressive force, the length of the sides decreases. So the volume decreases by delta V. Consider this as a body of volume V, and this is your final volume. So this final volume is equal to V minus delta V. Delta V is a change in volume or the decrease in volume. So I can define volumetric strain as the change in volume to the original volume. So this volumetric strain concept is used in defining bulk modulus. So this bulk modulus we will see in the subsequent lectures. So this is this all are the various types of strain. So first we have seen linear strain, then in linear strain we have studied what is the tensile strain and then compressive strain, and then we have studied shear strain, after that volumetric strain. Stress. Whenever anyone is asked about what a stress is, they will be giving the definition as stress as force by area. But you have to understand what this force is and what this area is. See, when your body is subjected to external forces, when your body is subjected to external forces, it gets deformed. So this all knows. So what happens internally? So due to these external forces, what happens is internal forces are developed within a body. Internal forces are developed within a body which oppose deformation, which oppose the deformation. The internal resistance force, the internal resistance force developed in the body per unit area is called stress. So I am having a body as shown in the figure. You are applying a force like this. So due to the application of force, what happens is forces are developed within the body. The forces will be developed within the body. So that forces are called as internal resistance force. So stress, it is denoted by the letter sigma, and it is defined by the internal resistance force. Internal resistance force per unit area. So what area you have to take? Consider two bodies. One is a body with rectangular cross section, and another is a body with circular cross section. So in both the cases, it is subjected to a force, opposite forces P. So the resistance developed in the body will be equal to the applied force. So I can say the resistance force is equal to the applied force P. So P divided by A. So what is A in this case? So area is the cross-sectional area. If you consider this as the thickness and this as the breadth, your area will be B into T. If you are using the stress formula for a rod, then your formula will become stress is equal to P by A, where area A is given by the circular cross-sectional area. So area A is given by pi by 4 d square, where d is the diameter of the body. What I have discussed is a normal stress. There may be also shear stress. So stress, you can classify the stress as normal stress, sorry, it is a sub-classification. First, you can classify stress as direct stress, indirect stress, the third one is a combined stress. This direct stress can be classified into normal stress and shear stress. The normal stress can be either compressive stress or tensile stress. And shear stress, it is indicated by the term tau. Indirect stress, it is developed due to bending and torsion. Indirect stress, it is developed due to bending and torsion. So you'll be having bending stress and torsional stress. The combined stress is a combination of direct and indirect stresses. First, we shall see what is a direct or simple stress. Yeah, simple stress is called as a direct stress because it develops under direct loading conditions. It develops under direct loading conditions. So what do you mean by direct loading conditions? You can take the previous example itself. You are having a body and I am applying some compressive force. So this compressive force is acting along the axis of the member. So the force is acting along the axis. So such type of problems in which the force is acting along the axis of the member, we can expect that direct or simple stress is developed in such bodies. So the formula is stress is equal to force by area normal stress. Normal stress, you'll be having two classifications, sigma T and sigma C. So this is your tensile stress and this is your compressive stress. See, the force is acting along the axial direction and the area. So this area is normal to the applied force. So for calculating tensile stress, you have to take force by area. So this area is the normal area. Normal area or normal, you can take this as normal or perpendicular to the applied load. So the area is normal or perpendicular to the applied a load. Like this, you can define a tensile stress or a compressive stress. In both this tensile and compressive stress formula, the formula is same, force by area. The area is always normal or perpendicular to the applied load. So that's why it is called as a normal stress. If you apply a compressive stress, what happens? The length decreases. The length of the member decreases, and if it is subjected to a tensile force, what happens? The length increases. So you can say it from the figure itself. Tensile stress means you are applying a pulling force. So what happens? The length increases. And compressive stress. For compressive stress, you will be subjecting the body to a two equal and opposite push. So the length decreases in the case of body subjected to a compressive stress. The third one is the shear stress. Consider a body like this. I have put a rivet in this. So this is your body. I have put a rivet in this. So if I subject this body to two equal and opposite tangential forces, what happens? The body will fail at this particular area. So the body will fail at this particular area. So at this area, the body will fail. So shear stress, it is defined as the shear resistance divided by the shear area. Shear area. So what is your shear area? So this is your shear area. If you are taking a rivet, it will be having a circular cross section. So the area will be pi by 4 d square. So this is a case of single shear because the body fails in one particular area. See, in the previous normal stress, you have taken the area perpendicular to the applied force direction. But in the case of a shear stress, the area is, this shear area is parallel to the applied load. This is a case of single shear. You may have double shear also. Consider a member like this. And another member is here. So these two members are connected by a rivet. So these two members are connected by a rivet. So you can assume the diagram, it is not exactly perfect. So two bodies are connected by a rivet. So what happens is you may have the body C failing at two areas. So one is in this area and second one in this area. So two areas the body will fail. So in this area one and in this area two. So such type of shear is called as double shear. So in the formula, what you have to do is instead of uh, shear stress equal to force by area. So this is a case of a single shear, but for a double shear, what you have to do is in the area you have to consider both the areas, area 1 and area 2. So both the areas you have to consider. So this area will be A1 plus A2, or you can say it as, if it is a uniform area, you can say it as 2 times A. Okay. So with this we can end this lecture on stress and strain.